Okay, the context here is status indicator lamps and why you might want to go around shooting lasers at them. If you shine a really bright light on them, all that energy has to go somewhere. Would you believe it flows backwards into the electronics? Effects range from nothing at all to remote code execution. It takes a fairly powerful laser to do it because in addition to information, you're also supplying all the energy needed to run the electronics in reverse. There are at least two different physical effects going on here: a photoelectric effect and a photoconductive effect. The photoelectric effect lets us change a binary 0 to a 1, but not the other way around. The photoconductive effect lets us change a binary 1 to 0, but not the other way around. This immediately suggests that the two effects might be used in concert, but the problem is some electronic components respond only to one or the other effect, but not both. So this places some fascinating constraints on the attacker, who might be able to change an instruction, a load instruction into a branch, or an add into a subtract, but he can't change a branch into a store or a divide into a compare. So we say he can execute arbitrary-ish code. It's a kind of weird machine. It's easy, for example, to redirect a memory access up into high memory. Just set the high bit of the address. So our attacker patiently watches the instruction stream go by on the bus, picking and choosing opcodes that he can alter into the instructions that he wants, slowly building up the desired program in high memory. Maybe it's not quite the program he wanted because certain bit patterns are unreachable. So the first thing the arbitrary-ish code does is run fix-ups on itself. Finally, we redirect a branch to the fixed-up code, and it's game over. The attacker must be very careful not to crash the running program because its memory accesses are needed to subvert. If the target computer ever crashes, access is immediately lost. Maybe I should demonstrate. This is a fairly simple computer. It implements the instruction set from the previous slide, but it's complex enough to illustrate the difficulty. It's a 4-bit CPU load store architecture with one register called the accumulator, which is visible over on the right-hand side, the 4 red LEDs. Think of this as a factory automation controller, reading pressures and temperatures, turning on motors to open and close valves in a chemical process plant, say. Normal operation is shown by a regular scanning pattern on the accumulator LEDs, left to right, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. The attacker needs to watch the target system for a while because timing is absolutely critical. The attacker watches the system in order to learn the cycle time and get a phase lock on the internal state of the CPU. This is possible because the accumulator display always changes at a known offset in the microcode cycle, which might be different for different instructions that can change the value of the accumulator, but the attacker can tell the difference by observing the magnitude and direction of the change. So the attacker just watches for a while, just observing the computer and getting a phase lock on the CPU. Once the attacker has a phase lock, the lasers begin to fire. You can't see the beam in this example because the lasers are ultraviolet, But you might be able to observe a little bit of fluorescence in the epoxy coating over the top of the LEDs. It only takes a couple of seconds. But note that the pattern on the accumulator display over on the right-hand side has changed. It is no longer doing the regular left to right scanning pattern. The pattern has changed, and the reason is because this computer is now running a completely different program, one that we inserted through the front panel status indicators. Okay, analysis begins with the electrical schematic, looking for potentially susceptible components in electrically interesting places. This is one of the constraints on the attacker because we can't choose where the LEDs are or how they're connected. And that determines what we can do. Not every indicator will do something useful if reversed. So here's an electronic component. Light emitting diodes are interesting because they're a naked PN junction. The basic building block of all solid state electronics. You put electricity in, light comes out. But there's a general principle in physics that any process that runs in one direction can often be made to run in the other direction if you supply enough energy to make up for the difference in entropy. When you put light into an LED, it comes out as electricity, but in the opposite direction from the usual current that makes it light up. This violates important assumptions made by the circuit designer. We can force the voltage on a communication bus high or low, depending on how the LED is connected, by hitting it from a distance with a laser. Now, the first question everybody always asks is, how far away can you do this? And the answer is, we don't know. I didn't put this in the paper, but the reason we don't know is because I suck at aiming. So we solved that problem. We aimed it once, and then we bolted everything down so it couldn't drift out of alignment. That's the answer. It is not my problem to figure out how to aim this thing. It's my problem to measure it. So we built this infernal machine. It consists of a pair of linear actuators. The x-axis one bolted on top of the y-axis one crosswise, so we can raster scan a focused laser across any desired component on the circuit board, stopping every 50th of a millimeter to measure the voltage on the communication bus. There's a live I²C bus under there, and it's communicating the whole time. Each linear actuator has a stepper motor on it, and there's a bank of relays that lets us automatically vary the bus voltage and the pull-up resistor value, so we can simulate all kinds of different kinds of circuits. The orange stuff is radiation shielding. Data collection is automatic, transmitted out by a serial connection. The whole thing is controlled by an Arduino. I like Arduinos. It's all C++. The hardware is relatively hard to accidentally fry, and they're cheap. So here's what the raw data looks like coming out of that machine. You're looking straight on at the LED. The big blue square is exactly 5 millimeters across. And that funny curving arc on the right, over on the right-hand side, we think is an artifact of the dome lens on the LED. We can draw isovoltage contours to visualize how the voltage on the communication bus varies as the laser scans across the face of the LED. We're looking for the physical location where the laser has an effect, where the laser can focus, can force the voltage on the circuit to go below the logic threshold. We're only interested in one of those contours, the 2-volt line, because that's the value we found by experimentation to be the critical value. This picture is where Professor Rasmussen got real excited. He calls this the active area. Any hit by the laser inside that contour line changes the value of a bit. You can actually see the square outline of the chip inside the LED, or maybe that's just my imagination. But he wanted to know the area inside that curve. This directly corresponds to how hard the target is to hit. This is one of those problems. Finding the area inside that curve is one of those problems in computer science that looks hard but isn't. It suffices to just sum over all the pixels in the image, counting the number of pixels whose value is less than 2. I felt like Alan Turing when I wrote that algorithm. Don't tell anybody, they all think I'm a whiz at physics, at calculus. But there's a problem. There's a problem with commercially available devices. Blinky lights are cool, but the hardware designer might not have put one where we need it on the communication bus. You can't shoot lasers at an LED that isn't there. But I don't want to give you the impression that it's only LEDs. It's not only status indicators. The definition of accessible PN junction is wider than that. For example, we found that electrostatic discharge protection devices, ESD, components on communication buses, which are there because communication buses are susceptible to ESD damage, we found that they are lots more sensitive than LEDs. Notice what you're looking here is the results of a lot of repeated runs against one of those components. Notice how the active area in red gets larger as you go down the chart, and it gets larger as you go from left to right. As the system voltage decreases from TTL to CMOS to low voltage CMOS to 1.8 volt LV CMOS, and as the value of the pull-up resistor on the bus, which determines the speed of the bus, changes, we can force the value. By the time we get down to the bottom row, we can force the value of a bit against any reasonable value of pull-up resistor. But note that the active area on this component is a lot smaller than an LED. That's a microphotograph in the upper left-hand corner. The chip is only about 125 microns across. It's a very small target to hit. It's also off-center in the gap, which makes it challenging to hit. But now we have a model that makes testable predictions. For any combination of LED color, logic family, and pull-up resistor value, we can predict if it's reversible. By the way, unlike LEDs, which tend to respond to visible wavelengths, we found that the most effective wavelength for silicon devices, ESD protection devices, is in the 900 nanometer range, which means it's invisible. That makes the attack stealthy. It's not isotropic either. This figure shows the effect of elliptical beam axis rotation on the active area. We have not looked into the effect of polarization at all. This apparatus will be out in the demo area during the poster session if you want to play with it, prove to yourself that it works. I want to thank my collaborator, Professor Rasmussen. When I brought this to you, it was literally 2 paragraphs and a funny-looking oscilloscope trace. He made it scientific. Finally, I want to thank the anonymous peer reviewers for being so harsh on us. There is not one claim left in this paper that we did not measure to 3 decimal places. And it's a better paper because of it. Thank you.